skip for now since you're there.
Okay, sure.
If someone complains that this is autofocus or something, just do that in the comment. But it looks okay now. It looks fine.
What should I do if it's autofocus? Like,
Go with this until it works.
Oh, okay.
Yeah.
Yeah, of course.
Yeah. Yeah, I think this. Hello, hello. It's okay. And there's nobody there. Let's see. I'll start in a second. Let me just write down these things. Let's start. And yeah, let me know if someone complains about the transmission. So today we will go back to the sprint post-selection paradoxes. We'll see explicitly how Hardy's paradox is an example, like step by step. And then we'll start talking about a new concept, which is this contextuality. In particular, we'll give the definition of a type of contextuality. We'll talk a little bit about what it means, and then we'll try to relate this notion of contextuality and non-contextuality with these paradoxes. Okay. So just to recap, if you remember, the way we define this logical print post-selection paradox was that we have an experiment that has some pre-selection, meaning we prepare some state. Then here in the middle, we'll make some measurement, P, and then we post-select on something else, right? And we say, well, we start with a small number of projectors, which represent the things that we can actually measure in the lab, a minimal set, and then we expand this set now by adding complements and adding products of things that commute. And then we say, well, now we try to assign a function to every element of the set, to every projector in the set that acts like a probability distribution. In particular, it should recover this ABL probabilities. So it should behave in this way. And then it should also behave like a probability distribution, right? And we said that it had these properties. This one here, I came up with a couple of exercises for you to do in the tutorial to see that from here you can recover, just usual like probabilities of joint sets and disjoint sets and so on. that these things can come from this thing, okay? And then we said, well, they're logical print post-selection paradoxes. So the print post-selection paradox is if you cannot find a function that satisfies all these things. And we call them logical in particular if the outcomes of the original measurement were 0 or 1, okay? If the ABL probabilities for the intermediate measurement were 0 or 1. And in fact, I had a look at it, and it's sufficient to say that they are 1, okay? We don't need to worry about the zeros because the zeros come for free because you don't put for every projector in the original, in the original set, you add the complement as soon as you build this larger set P prime. So that's okay. So we can restrict ourselves to this case. By the way, I scanned all the lecture notes and I sent them to Ralph, so they should be uploaded sometime during this lecture, except the ones from today. Okay. So now let's see again the hardest paradox this time, even simpler than what I did yesterday. So hardest experiment as a special case. And this time we actually compute all the probabilities. Okay, so we have this initial state we already know. Final state was this minus minus. And in fact, I was trying to figure out the simplest way to do it, and we can have on our original set P just the thing in the middle corresponding to just Alice measuring her qubit or just Bob measuring his qubit on the Z basis. Okay. So with PA being then projected into outcome 0, PB being the projected into outcome 0 of Bob. From here, already get all the. We'll see that we already get all the projectors in the larger set that recover the paradox. Okay. So you remember the setting. So they prepare this joint state, Alice and Bob. At the end, they post-select on this outcome by measuring, on the local X basis. And in the middle, they can make a measurement. And we only need for now to consider the case where just Alice measures in the Z basis or just Bob measures in the Z basis. Because we'll see that now that these probabilities are going to be 1 for these cases, which is what we already showed before. Okay, so we'll do it. And please warn me if I make mistakes, because let me just write here PA. So let's do it for PA. So this is going to be PA squared. Yes. Okay. And now let's look at this nominator. So what is this? A2. We're just going to show, well, we'll show that this is 1. Okay. So we leave the selection alone for now. Now PA was this projected into 0 for Alice, nothing for Bob. Here comes our state. Okay. And if we look now just here, only one term survives, right? Just like we saw in previous iterations of this experiment, only this term survives. So then we have So this is 1 over square root of 3. And now let's write what this is. This is minus 0, 1, right? Now I'll just write this in a more friendly way. Okay, I'll just do this directly. Minus 0, minus 1. Okay. So what are these overlaps? Right, this is 1 over square root of 2 and minus 1. It's going to be minus 1 over square root of 2. Okay. So 1 over square root of 2 times minus 1 over square root of 2 is minus 1 over 2. So you get minus 1 over 2 square root of 3. Okay. Now we'll do the other one. I will do it down here. So now we need this thing, and we look just at what's inside the absolute value. So we have this identity minus PA. Okay. So this is going to be this minus what am I doing? Okay. This thing, we know what it is. Right, so and now this thing here, we need to compute this overlap, right? That's actually not how I did it in the lecture notes. I did it in a smarter way by putting here the, yeah. Look, we can do this and we'll see that this overlap is precisely that. Or we can do it by writing what this projector is. It is just one tensor the identity. And that's actually an easier calculation to do. I don't know about easier, it's less annoying. Identity, over square root of 3. No, yeah, this is much nicer. Because then we do this grouping again. So what elements survive here? We're projecting into 1 in the first qubit. So only these two survive. So we have 1 plus 1 0. Okay. So we have 1 over square root of 3. This thing is going to be minus minus. And now here we have 1 and 1 plus 0 is plus times square root of 2, right? But now we have the overlap between minus and plus, and we know that this is 0. So we get square root of 2 over 3 minus 1. This is some number, but now we have here minus plus, and that's 0. Okay, it's easier to do it this way. So then we prove this, right? Because this is a constant, this is the same constant, this thing is 0, this probability is 1, right? you can do exactly the same for the other one. With symmetry, same thing. Okay. And then the only one left to do, well, now, okay, so now we're in the conditions of talking about a logical pre and post-selection paradox because we have this small set where all the probabilities are 1. So now what's in the bigger set? Right. So the bigger set has first all the complements of those things there. Second, if 2 elements commute, you can have the product of them. Right? So then it includes things like so of course it has the original ones. Because these 2 commute, we can also have the product. This is allowed by the rules of the definition. And then, of course, you also get all the complements. So you get, for example, identity and etc. The only one that we care about is the one that we used when we talked about the paradox before, which is this one. This is the probability that they both get 0, right? And this we can compute very easily that this is 0. Okay, so F. Equals 0 because, so we just apply this same formula again. Sorry, 0. This is again this 1 over square root of 3. And then comes in 0, 0, 0, 0. Apply to this data, there's no 0, 0, right? This is 0. And then, of course, one is to show that the thing below is different than 0. But this we can do. And then now we need to find the paradox, right? So now we need to find a contradiction with this things. Right? So now we have the function defined for these 3 operators. Let's call this PAB. How do we find prediction? So we have and we know that PB is this new projector. And we know that we apply this third condition, so F of PA plus PB minus PA PB. By condition number 3, this should be F of PA plus F of PB minus F of PB. That's 1 plus 1 minus 0, that's 2. And that's in contradiction with this condition, right? Contradiction with condition 1. Is that clear? I just say, okay, we found this function, we computed for these 3 projectors, and now we'll see what happens when we apply this rule here. Okay? And what we have not convinced you yet is that this rule is very natural, and this is what you'll do in the tutorial. And this later on, when we'll talk about weak measurements, we will see that in fact these strange values like a kind of probability that is 2 actually relates to something that you can measure in the lab. Okay. So it was just an example. Good. Now we start talking about something completely different. And we'll start relating the two. Okay. So I hope between this and the examples you did in the tutorial, you're kind of convinced that this definition of these paradoxes captures like the strangeness in all these examples, the things that don't seem quite right. And now we kind of explain, with this new definition, we explain the intuition for why they don't seem quite right. What part of our classical intuition do they clash with? So, and that's the notions of quantum contextuality. So what is a non-contextual model? This is like a hidden variable model for your experiment. Okay, it's saying, oh, we have this theory that's quantum mechanics, but maybe there's some reality under that would give us better statistics if you had access to this, in the same way that in thermodynamics, you say, oh, maybe we only have access to pressure and volume, but there's an underlying theory, like the theory of gases that, if I knew the velocity of every particle, I could get much more information, right? And it's one that is, you talked about this for local hidden variable theories, and this is a very different constraint, which can be related to that. Okay. By the way, people these days don't use so much hidden variable model. They call it ontological model. So in general, we talk about, in foundations, whenever you hear the word epistemic, this refers to knowledge. And whenever you hear ontological, this refers to reality. Okay, so it's like a model of reality of what's behind the quantum state. And the assumption is going to be that is independent of context, and we'll see what this means. We'll see what this means, okay? So let's first talk about this model, what it is. So in quantum mechanics, we have a quantum system described by saying Hilbert space and states here. And now we say that what's really behind in nature is some set. So this is just a set of what we call ontic states. Ontic just means real. So this is like, this is the reality under the underlying reality. In the sigma algebra, which really is just a fancy way to say all the subsets of this thing, right? Oh, a description of what subsets we can consider. So I'll just write here. Oh. Then in quantum mechanics, you can make some preparation, meaning you prepare a quantum state, or you prepare not a pure state, but a mixed state, or we can even have like a more, not even a quantum. I'll write here prep. Not a quantum description, but just an operational description, meaning, oh, it's whatever state is prepared when I press these buttons in the lab. Okay, it's like saying, I don't want to model this. And then what does our model tell us that's happening in reality is the following. It's like, oh, if I think I'm preparing a state, here are all the real states, okay? And if I'm preparing a state, what I'm doing is picking from some distribution one of these real states at random. In the same way that in thermodynamics, right? If I say I have a gas at a certain volume and pressure, if you look at the statistical description of this, what it means is a flat distribution over some set of states, right? Whereas here is like all the microscopic variables, right? So this would be this, right? So this, for example, would correspond to state, and then this would correspond to some other state. Okay. And how do we formalize this? Well, we say that every preparation induces a measure. I'm writing now as if it was a pure state in the quantum description. So measure mu on my set of context states. And what's a measure? It's a measure, you know. It's something that lists, that maps any subset to the real numbers, and you know, is always larger than 0, and it's 0 for the empty space, and it's countably additive, meaning that if you take the measure of two disjoint sets, is the sum of the measures, and so on. And we'll see in a moment how this is relevant. Okay, for now we can just keep, yeah. So what I'm saying in the graph is in the same way that in thermodynamics you say, well, if I prepare a gas at some pressure and volume, we know that in reality you're preparing a microscopic thing, but you don't have information about which one, right? But you know some parameters of this, right? We have some bounds on this. So what you do is preparing, in reality, it's one state that is picked at random with some probability, and the probability is given by these microscopic parameters. In the same way, what these models, these hidden variable models or ontological models do is say, if I'm preparing a quantum state, this is like my macroscopic variable. In reality, I'm preparing one of these real states. I don't know which, but each state determines is like, what's the probability measure that I'm drawing for? Yeah.
So just I get this right, it's a hidden variable model,
yeah,
but it's not like a classic hidden variable model. It could be in theory also quantum.
It could be anything. At this point, it could still be anything, right? I mean, this could even be just in one-to-one relation. Like you can make the hidden set to be just again the Hilbert space, right? At this moment, it's still completely general, right? We have not imposed any constraint, but now we're going to impose some constraint. And that's what's going to make it a non-contextual model. So again, on the left is the quantum case. So if we have a measurement, we describe it in general by a POVM. Later, we'll talk about projective measurements, okay? Some set of positive, semi-definite positive matrices satisfying that we sum up to the identity. Okay? For example, in a projective measurement, this will just be the projectors. Now, and how do we determine probabilities? Well, the probability of some outcome k for some state I. Okay, right. And if it's a mixed state, so how do we do this in the quantum, in the what is called a measurement non-contextual model, is saying for each of these operators, okay, that correspond to an outcome, we associate a probability distribution. So I use prob for the quantum one and PR for the ontological. On the stage, on the real things, okay, on the real states, meaning that when I make a measurement, what I'm actually measuring, of course, is one of these real states, okay, which is picked with some probability, which depends on the preparation. Okay. So, and how this is connected is saying that then, well, first we need to satisfy that the sum of all case. Sorry. The same thing again, just like if I'm measuring a quantum state, if I'm measuring the real state under the sum of all outcomes the sum of the probabilities of all outcomes must be 1. Yeah?
What assumptions are we making about the overlap among the measures of?
We are not yet. There's a lot of funny results about this, yeah, right? But in this case, we're not talking about this at all, okay? Not yet. And then how do we connect it to the probabilities? Well, we say, you know, what we're actually measuring is the real state. So the probability of getting an outcome, it's going to be the product of the probabilities of getting an outcome given the real state times the probability of actually measuring that real state, right? Okay. Does that make sense? This is just like probability distribution, and we say this thing must be equal to that. Okay, so say this. This is how we connect the quantum thing, like the quantum statistics, to the underlying model. And this, although it might look very innocent, this is the assumption of measurement non-contextuality. Okay, so this is there's many notions of non-contextuality as researchers studying them, maybe even a bit more. In particular, there's also preparation non-contextuality, and there's other less operations. This one is tying it to the measurement itself. And what does it tell us? Well, it tells us that the probability of getting some outcome only depends on this, like on this operator. If it was a projective measurement, only depends on this projective, and it does not depend on how you implement the measurement. Okay, so it does not depend on what the other projectors inside the set of the measurement would be, which is like the context of the measurement. Now, this may seem a bit empty, so let's try to see some consequences. And you'll see already oh, this will be related to our paradoxes. Right, so essentially it tells us that the probabilities really only depend on this POVM element, don't depend on how the measurement is implemented. So in particular, suppose that we're talking about coarse grainings. Okay. So examples. what do I mean by coarse graining? I mean, there's a global measurement that is more complete, and then we just forget one of the outcomes. So for example, both Alice and Bob measure their qubit, but now we only care about the probabilities of Alice getting an outcome. Okay, forget about Bob. More explicitly would be, so suppose that we have the larger measurement described by some QVM elements. Think of projectors, it's easier, but it is more general. And now suppose we have a smaller measurement described by a smaller number of projectors, and these are given by J, E, J, K. So for example, so suppose I have a ZZ measurement. So what are the possible outcomes? They both get 0. Alice gets 0 and Bob gets 1. Alice gets 1 and Bob gets 0. Or they both get 1. Right. Then you could think of like a smaller measurement just on Alice, which is taken as a coarse graining of this thing. Right. So just and here each of these projectors is given by a sum of these two, right? So this is 0, 0, 0, 0 plus 0, 1, 0, 1. And this one is 0, 1, 0. So if we have something like this, and we're using that assumption, then of measurement, this model of a non-contextual model, then the PR of Zook is just a sum on J. The PR of lambda. Okay. And this is why, this is again because, you know, now even if this measurement was not, even if Alice is doing a local measurement and Bob is not doing anything, according to this kind of models, these probabilities must be given by these marginals. And that's precisely because, you know, the probabilities must be them no matter if we implement measurement. So you can always think of, oh, I implement actually the global measurements, so I have these distributions, and now I just take the marginals of the statistics to get those distributions, right? So this follows from the thing. And here you can already see that, for example, in the case of Hardy's paradox, we didn't have this behavior, right? Because we had we had the marginals being 1 and the global thing having probability 0, which, like, we'll see later that this is not compatible with this assumption. And the other one is that when measurements are obtained by mixers, then again, same thing. Okay, so as probabilistic mixtures, meaning the following, that if I have, say I have two measurements, and I can mix them to make a new measurement, meaning the following, where EK then I'll give you the intuition for what this means. Then what is it? Okay. Lambda. Q. Okay, prime. So what would be, okay, well, first of all, what would lead to this conclusion? This would be the case of saying, well, one way, if these measurement operators can be written like this, then one way to implement this is to throw a coin that is biased with probability Q. I get heads. In that case, I implement my measurement M prime with probability 1 minus Q. I get M prime prime. I implement this, and then I just erase the information of what I got heads and tails, and I just record the outcome of the measurement. Right? And that's one way of implementing this more mixed measurement. So from that implementation, you can conclude this. And now what this tells us is that, like, even if this measurement was not done by mixing two other measurements, then it should still satisfy the statistics. Okay. So let me try to think of an example. Yeah, I'm not sure this will be true, but yeah. I don't have a nice example at hand. You could think of here like Alice measures in base Z and Bob in base Z. Here Alice measures in base Z and Bob measures in X. And in this case, like Alice doesn't know exactly in which basis Bob measured. Okay. This is, yeah, two literal example. Okay. So I will now state the result that we will spend the next lecture proving. So by the way, quantum theory is clearly contextual. So there's many proofs, many experiments one can make that show that for many settings, you can have a non-contextual model of quantum theory. Okay. It's just not compatible with the measurement statistics. And these are usually cleverly engineered experiments. And if you want to learn about this, come to the summer school because David Schmid will talk a lot about it. And in fact, non-locality and Bell inequality violations can be seen as a violation of non-contextuality. So what is the theorem? This is a theorem by Matt Leifer and Matt Pusey, the other way around, which is logical pre- and post-selection paradoxes are some contextuality. Or in other words, if we have a non-contextual model that is compatible with the statistics, of some experiment, and we have the probability of P. Again, these probabilities are all 1. Then we have no paradox. And okay, so this really connects these two notions. Like what's strange about then we'll see that what's strange about all these experiments that we looked at is that they don't admit this kind of model, this kind of simple underlying model, right? Where we just say, oh, think of the quantum state as some statistical description of the underlying reality, and think of the outcome probabilities as this mixture of probabilities for the real state that's underlying, and make this depend only on the projector. That's not true. That's why we cannot build this larger probability distribution that behaves like a probability distribution. Okay, and the proof that we'll do next time is in two parts. So first, we will connect. The proof will be. I'll just write what we'll do. We'll connect the probability in the ontological model with the probabilities of P with the quantum probabilities. Okay. We're going to say, oh, if there's such probabilities that are zero, that are just 0 or 1, then we can kind of connect this to some underlying model that takes into account not just the pre-selection, but also the post-selection. And then we see that these things are well behaved, meaning this ontological probabilities, they really are by definition probability distributions, right? So they behave like probability distributions, which means that they satisfy all these conditions so that we don't have a logical paradox. Yeah. Okay, so we'll start the proof next week. It's a nice proof because it shows you kind of what kind of tools people use in foundations. Good. All right, we stop here for now. Thanks.